السلام عليكم ورحمة الله وبركاته.
عليكم السلام ورحمة الله وبركاته.
How are you يا شباب؟
وعليكم السلام ورحمة الله وبركاته. How are you, doctor? Fine,
Yeah,
doctor?
I'm fine. What about you?
Alhamdulillah. I am fine.
Well then, as you can remember, we are now on this is the third week, right? So the next 3 weeks we'll take major one. So I hope you have started preparing. And today we will take our first quiz. And then tomorrow, next week will be our second quiz, because next week will be week number 4. So we will have our second quiz on week 4. Okay? Correct? Yeah, okay. So now, major is week 6. I posted the major schedule. It's on 6, I think, on this Sunday or Monday. Okay, at the beginning of week 6. Okay. Today we will have lab at 2, although you have been divided into 2 groups. Okay, you have been divided into 2 groups. I will send you the grouping immediately after the class. Okay, there is group 1 and group 2.
Doctor, same time or separated time?
Different times.
Okay.
Yeah, we were asked to make it at different times. It's 3 hours, so 1.5 hours, and then one is 2 hours 20 minutes altogether. So the first group will come for the first 1 hour 20 minutes, and the second group will start immediately after that. So the first group will start at 2 and finish at 2:20. Sorry, at 3:20, and the second group will start at 3:20 and finish at 4:40. Okay. Is it clear?
Yes, Doctor, who's in group 1 and group 2?
Yeah, always there will be group 1 and group 2 because of the spacing. You know, the lab is not so big, so you are 14, so we were asked to divide you into 2 groups. The grouping has already been done. Immediately after this, I will post on the WhatsApp group, okay, the different, so that you know when to come, okay? And okay, so let's continue from where we stopped. Okay, and I will share my screen. So in the course of my discussion, if you have any question, you can just let me know. Okay, you can talk. You can just talk. Your mic is already enabled, so that I can just respond to whatever question you have. Okay. All right. So let me share my screen with you. Right. Not water balance. Did you watch those videos? Gentlemen? Okay. All right, I can see it is sharing. No, the quiz is not on in the laptop. You will take it during the lab hours. Okay, it is not online. When you come to the lab, you will first be given the quiz, after which we will take the lab. Okay, so that's the first thing you do. All right, today we'll look at conversion of point precipitation to aerial precipitation. You know, when it rains, probably sometimes you hear in the weather forecast that is good, like maybe if it rains, let's say in Hafrul they will tell you the intensity of the rainfall maybe is 2 inch per centimeter, okay, or 2 inch. That 2 inch is not the same everywhere. It's more or less like some kind of averaging over the whole drainage area, over the whole catchment area, that the rainfall or that the precipitation occur. Okay. Now we will look at how to convert point precipitation to aerial precipitation. Point precipitation here refers to the rain gauge measurement of rainfall. Okay. We measure rainfall or precipitation using rain gauge. I already provided 2 videos for you to look at how this manual and I think there is also one for automatic recording rain gauge, how they work. Okay, I've already provided you with this. And I hope you have taken your time to watch it. So now these rain gauges, you see, they are at points. I mean, they do not occupy the whole area. They are at some points, at some intervals here and there. So how do we now convert the readings from those rain gauges to present the average precipitation over the entire catchment, over the entire drainage basin? Okay, so this is what we are going to look at here. Here we will look at some readings from some different rain gauges at some different areas within a given catchment, and then look at the methods by which we can now use the readings from those different rain gauges and then convert those readings into aerial precipitation. By aerial precipitation here, it means like the precipitation over an entire area. Okay, so the representative precipitation over a defined area is required in engineering applications, whereas gauge observation pertains to point precipitation. Gauge observation here refers to the readings we get from the rainfall gauges, okay, from the rain gauges, okay. And then the aerial precipitation is computed from the record of a group of rain gauges within the area by the following methods. So these are the methods that we use in computing the aerial precipitation. First one is the arithmetic or station average method, and number 2 is weighted average method. Under the weighted average method, we have 2 types: A, Thiessen polygon method; 2, isohydral method. We will look at the second part, the Thiessen polygon and the isohydral method, while we will explain about what is, how do we carry out the arithmetic or station average method. Now, the arithmetic or station average method, as the name implies, arithmetic or station average method is a simple method which consists of finding the arithmetic average of the values of the precipitation for all stations within and in proximity to the area. So you have different rainfall stations, let's say one in Muhammadiyah district, one in Al Khalidiyah, one in Al Baladiyah. Okay, we know that rainfall occurs at different intensities on different locations or in different locations. Okay, so if we have these rain gauges spread over different locations, we simply get the average, all the rainfall values from those stations, and we use the average value as the areal precipitation over that entire area. Okay. This method assigns equal weight to all stations, irrespective of their relative spacings and other factors. Other factors are, for instance, the rainfall duration, because rainfall duration more often than not is not uniform on all areas. It may be raining here in the university, while it may not be raining, let's say, in Al Makan Mall, or let's say in Sara Mall, or in Hala Mall. Do you get my point? Or it may be raining here in the university, it may still be raining in Al Makan Mall, but the rainfall intensity will not be the same. While it may rain here, let's say 20 minutes, it may rain there for, let's say, 15 or even 30 minutes. And that tells you that the precipitation over the areas are not equal. And the arithmetic average is more or less extremely simplistic and doesn't take care of a lot of other factors, such as the rainfall duration, the rain gauge spacings, and other practical factors that influence the precipitation. Okay. Now, the Thiessen polygon method. Thiessen is the name of the scientist who came up with the method. Okay. So this method it is using weighted average. Okay? It is using weighted average, and in this method, weight is assigned to each station in proportion to its representative area defined by a polygon. So we have like a representative area defined by a polygon for each rain gauge. Okay, and that area is like the area covering that particular rain gauge. Okay, we are going to take example, and I will explain more on that. These polygons, how are they formed? They are formed as follows. The stations are plotted on a map of the area drawn to a scale. We will check it in figure 2.4. Okay, so we place the stations on a map. Let's say if we take like Hafral Babin, where the stations are, just like when you are navigating through, let's say Google Maps, you want to find fuel station here, restaurant here and there, so you can locate the rainfall stations as well. The adjoining stations are connected by dashed lines, and perpendicular bisectors are constructed. Perpendicular bisectors are then constructed on each of these dashed lines, as shown by the solid lines in figure 2.4. We will soon open figure 2.4 and we will check all this. Okay, let me open it here. All right, the area of each polygon is determined and then multiplied by the rainfall, the value of for the station within the polygon, and then the sum of item 5 is divided by the total drainage area, which provides the weighted average precipitation. Okay, I will take you through again with on the figure so that it will be clearer. All right. So this is the Thiessen polygon. Okay, you can see A, B, C, D. Okay, let me circle them. Let me increase the weight of my pen. Highlighter. All right, let me just, okay, so you can see A, this is rain gauge A, B here, C, D, E, F. Okay, so you can just imagine these areas, this map, if you assume this map is Hafral Batin, let's say A is where the university is located, B, let's say it's Al Makan Mall, C, let's say it's Hala Mall, like that, different areas on a representing different parts of the same catchment. Is that clear? So, and you have G as well in the middle. Okay, so the first thing you do, the first step says you plot these rain gauges on the map, which is this, and then the adjoining stations are connected by dashed lines. You try to join the station by dashed lines. You can see A is joined to B, to G, to F, okay, by dash line, okay, and C is also joined to B, to D, and to G, also by dash lines, okay. And then these dash lines, you now divide them. That is the perpendicular bisectors. You construct a perpendicular bisector on each of these dashed lines. Okay, bisector is a line that divides another line into two equal parts. Okay, and perpendicular means the line should be at 90 degrees. Okay, so let's start. When you go from A to B, this line, you divide it into two using a perpendicular line, which is this one. Okay, so this line is the perpendicular bisector, which is at 90 degrees. You do the same thing, A to F, which is this line. A to G, you divide it also using this line, which is at 90 degrees. Okay, this is at 90 degrees. F to E, you divide it using this line, which is at 90 degrees. E to D, you use this line, which is at 90 degrees. The same thing, C to D, you divide it using this line, which is at 90 degrees. Okay, and then C to G, you divide it using this line, this one, okay, this one, okay. So these bisectors, they will meet somewhere, okay. So that is why you can see where they and one here, you know, okay. All right. So these bisectors, they form polygon around the rain gauges, okay, and then the area of each polygon is determined and then multiplied by the rainfall. Okay, it is determined and multiplied by the rainfall. So the area here, because this is a map and it has its own scale, see the scale here, 1 inch is equal to 25 miles. Okay, so if you take A, so this is the area, meaning this rain gauge A is representative of this area under the polygon. That is this polygon. Do you get my point? Okay, so this is for rain gauge A. So we calculate the area based on the scale and multiply by the rain gauge value. The same thing, this F is representative of the area under the polygon, which is this. Okay, the same thing for E. This is the area for E, the polygon for E. Okay, for D, for G, this is the polygon for G. Okay, so we find the areas for each and multiply the area with a particular value of the rain gauge. Okay, and then we sum it up and then we add everything up and divide by the total area. So that's why it's more like multiplying the PI by AI. Okay, and then divided by the sum of the area. So this is the precipitation for a particular rain gauge, and this is the area covered by the rain gauge, and then you sum this up, okay, and you divide by the total area. So you can see that if you divide by the total area, dividing by the total area will take care of the total area that you added here, and then you will be left with what is called weighted average precipitation. Do you understand? I will give you an example here, very simple one, which will demonstrate. Okay, let me see. Okay, before I explain the isohydral method, I will give the example. Okay, let me explain the isohydral method and then we will take the numerical example. Okay, so the isohydral method is also another weighted average method, okay, but it is the most accurate of the three methods and provides a means of considering the orographic or the mountains effect. Okay, the procedure is as follows. In this case, the stations and rainfall values are plotted on a map to a suitable scale, similar to what we did for the Thyssen polygon method. But here we use contours of equal precipitation or isoheights. Okay, equal precipitation. We try to draw contours. Okay, contours of equal. I'm sure you might have done contours even in civil engineering drawing. Yeah, in civil engineering drawing, I'm sure you have learned how to draw contours. Let's say lines that represent the same value, let's say the same elevation, the same rainfall, you know, this and that. And you might have done contours probably also in surveying. I'm not sure. Okay, so you draw contours of equal precipitation, and these contours are called isoheights. Isoheights, okay? So these are drawn, and the accuracy depends on the construction of the isoheights and the interval. And the area between successive isoheights is computed, okay, and multiplied by the numerical average. The area between the isoheights is computed and multiplied by the numerical average of the two contour values, or the numerical average of the two contour isoheights. Okay, I will demonstrate that similar to what I did for the Thyssen polygon. And the sum of item 3 is divided by the drainage area, okay, which provide the weighted average precipitation. Okay, let me demonstrate it using a map as well, similar to what I did for the Thyssen polygon. So now here you have rainfall stations or gauge station. You can see one here, 2.1, 3.1, 4.5, 5.2, 3.8, 5.2, 3.3. Okay, all these are gauge stations. That is where you have rain gauges measuring precipitation. Is that clear? So we now use the values of these rain gauges or rainfall stations to now try to assume some contour lines, that is, lines of the same precipitation. Now, this is 5.2, this is 3.8, okay? This is 4.5, meaning as you move up, it is decreasing. So if this is 5.2, 5 will be somewhere here. So we now have a contour line, 5, okay? If this is 3.8, 4, and this is 5.2, this is 4.5, then if you move up, it means the rainfall intensity or the precipitation is decreasing. So if this is 3.8, then this is 4, okay? The same thing here, this is 4.5, this is 5.4, so this is 5 again. Now this is 4.5, this is 3.1, so this is 4 contour isoheights. Okay, the contour lines are the isoheights. Okay, so this is 4 and this is 3, and then this is 2. Now what do? We now find the area. What is the area here? Okay, what is the area here covered by this isoheight? What is the area covered by this isoheight? Okay, with respect to the drainage area, because we have to use the map, we don't go outside it. Okay, so what is this area, what is that area, what is this area, what is this area? Okay, so this is what we do, and we multiply the area here by the average of the isoheights. Okay, like the area here in this case, we multiply the area in this case by taking the average. This is 2, this is 3. The average of 2 and 3 is 2.5. So multiply the area by 2.5. When we move to this area, we multiply the area here by the average between 3 and 4, which is 3.5. Okay, so we will demonstrate this in the example. Now, the rain gauge's location in and around a drainage area are shown in figure 2.4. Figure 2.4 is the previous figure, okay, for the Thyssen polygon, along with the rainfall recorded at these stations due to a storm. Storm also is rainfall, okay? We call rainfall with different names. We call it storm, we call it precipitation as well, okay? Determine the average precipitation for the drainage area by the arithmetic method, and B, the Thyssen polygon, and C, the isoheightal method, okay? They may differ, usually they differ, but the difference between the methods may not be very significant. But like I mentioned earlier, the isoheightal method is the most accurate one, okay? So figure 2.4, this is figure 2.4. which shows the rainfall. Okay, so here we just take the average of all the rainfall values: 2.1 plus 3.3 plus 5.4 plus 4.5 plus 3.8 plus 3.1 plus 5.2 divided by the total number of the rainfall gauges. Okay, and that gives us which is simply total precipitation over the number of the rainfall gauge of rain gauges. Okay, simple averaging. Okay, which is exactly what is done here. Okay, 2.1 plus this or 7, because you have 7 rain gauges. Okay, 7 stations. Okay, so that gave 3.91 inch. Okay, 3.91 inch, which is using the arithmetic method. Now we will find the same average storm using the Thyssen polygon. And in this case, these are we have 3 columns: the observed precipitation in inch, okay, and then area of the polygon. Okay, so these are the area of the polygon which I cycle. Okay, and then we multiply column by column 2 to get column 3, precipitation times area. So 2.1 times 735 gives 1543.5, like that. And then we add this up to get this value. Okay, and then this is the total area. We add this to give us the total area of the catchment. And then the average precipitation is now column 3 over column 2. Okay, which is simply saying summation pi ai divided by summation a. So this is now 4 inch. You remember in the simple average method, we obtained 3.91. So this is 4 inch. So the difference isn't that significant. Now let's look at the other method, the isoheital method. The isoheital method, if you look at the figure, okay, the isoheights, okay, the first contour is 2, okay, and then we don't have any rain gauge after that. So we start from less than 2, 2, 3, 4, 5, and then greater than 5. Okay, and then covered by the isoheight. This is in mile square. The areas are provided in mile square. Okay, they're provided in mile square. So the area here less than 2 is provided as 0. Okay, area covered by the isoheight. Okay, and here the area covered by the isoheight 2, the area covered is 125. Okay, 125. Area between 2 isoheights, meaning here the area between 2 isoheights, that is before and after 2. Before and after 2, you have this area 125 and 820. Okay, 125 and 820. Let me go back and show you this 125 and 820 on the graph or on the map. Yeah, so this is now 125 and this is now 820. Okay, and then this is now 1 level red. Okay, and this, that is after 4. This one is 255, 2555, then greater than 5, meaning sum total this one and this one. Okay, because this is 5, this is 5, so greater than 5, all will add up to give us 500. That is this plus this. Okay, they will add up to give us 500. Okay, all right, let me go back to the table. All right, so this is the average value. okay? Area covered by the iso height, okay? This is okay, well, because this is started from 0. This is the iso height, and this is the area covered. For less than 2, the area is covered is taken to be 2, okay? So here we have this value, okay? Between 2 is so this, we add everything up, the area between the two iso heights, we add this up, okay, to give us 5,100, okay? And then the average of 2 iso heights, here you have, this is estimated because we don't have the value for less than 2, okay? So it is estimated to be 1.8. Then between 2 and 3, you have 2.5. 3 and 4, you have 3.5. 4 and 5, you have 4.5, okay? .5, and then 5 and greater than 5, you have 5.2, because this is the last value that you have, or more or less the average, because what you have is from 5 you have to 5.4, okay? So 5 to 5.4, the average gives 5.2, okay? And then we now multiply this out, column 3 by column 4, okay, to obtain this, and then we add them up, and then we divide to give the average precipitation. So you can see the value is 3.96. The previous one for the decent polygon is 4.0 inch. The arithmetic method, we obtained 3.9. So you can see they all agree to some extent. The difference between any two is not that much. Okay, the difference isn't much. So anyone you use will serve the purpose, except like I mentioned, the isoheital method is the most accurate. Okay. Now, any question before we move to the next chapter? I will today I will make homework 1 available. Okay, I will make it available so that next week when you are coming for the practical for the lab, you bring your homework in hard copy. Okay, you solve it in your handwriting, and then you type. You have a cover page, everything, and you use A4 only. You use A4 and you don't write front and back. You write on one only front only. Okay. You use A4 size, A4 paper only. Okay. A4 paper only. I will make the homework available today, and it will be due next week. You have to bring it during the lab. Okay. All right. If you don't have any question, we will move on to the next chapter, which is we are done with precipitation here. We will move to the next chapter, which is evaporation. Okay. Okay, let me share it. I will share the screen. and I will upload our application. I will upload the slide. All right. So, considering in chapter 2, we looked at the water cycle or hydrologic cycle, where we explained the cycle from rainfall or precipitation down to runoff, seepage, groundwater flow, runoff, and then stream flow, and then evaporation and transpiration. So now we will look at evaporation and transpiration, explain what they mean, and then the simple methods of computing them, and on to the next chapter. Okay. So here the intended learning outcomes are: you should be able to, you should, the end of the class, be able to explain the process of evapotranspiration and determine the amount of water lost due to evaporation. And evaporation, I told you, if you remember, is the main source of rainfall. I mean, the main source of water back to the atmosphere, because water evaporates from water bodies, from ocean, okay, from open water surfaces back to the atmosphere. And also we have transpiration taking place from plants, okay, through tiny openings called stomata. So evapotranspiration is the main input into precipitation, okay? Is the main input or the only input for precipitation. In this figure by the right, you have what is called the evaporation pan, okay? Or what is used to measure evaporation, although there is wind vane as well at the top, measuring the speed of wind. Now, reading quiz. Evaporation takes place at A, boiling temperature of water, B, freezing temperature of water, C, all temperatures, D, specific temperature. So I want each one of you to key in your answers, okay? Type your answers. Yes, I'm waiting. Type all your answers. I need each of you to respond to this. Let me check yours now. Ahmad Harun. A, but I think C is also true. You need to choose one. You cannot double, you have to choose one. Ahmad Harun. You have to take either A or C. Okay. So meaning all of you have chosen A. All right, let's see. Let's see. Let me go back. If you remember when I was explaining the water cycle or hydrologic cycle last week, I told you clearly that evaporation takes place at all temperatures, not only at the boiling temperature of water. Of course, the rate of evaporation increases with temperature, meaning it is proportional to the temperature of water. Okay, the higher the temperature, the more water evaporates. But Even if water is frozen, in frozen state, evaporation still takes place. You know, just bring out an ice cube from the refrigerator, from the freezer, and you will see, you know, the moisture, you will see water evaporating. Okay, so evaporation takes place at all temperatures. But like I said, the rate of evaporation increases with temperature. The higher the temperature, the more evaporation you have. Is that clear? But it takes place at all temperatures. Okay? Then let me see what you are writing. All right. Okay. All right, let's move on. Water loss to the atmosphere. Precipitation that does not ultimately become available as surface or subsurface runoff is called water loss. Okay, part of the precipitation that does not become available as surface or subsurface runoff is called water loss. Okay, and it consists of evaporation. One of them is evaporation, because evaporation is neither a surface flow or subsurface flow, isn't it? So it's part of the water loss. So it consists of evaporation, which is the amount of water vaporized into the atmosphere from free water surface and land areas. Okay, free water surface and land areas. And then you have transpiration, which is the water absorbed by plants and crops and eventually discharged into the atmosphere. They absorb water through their roots, okay, which is buried into the ground, okay. So they absorb water and moisture from the ground, okay, from the water available in the ground, okay, through the soil moisture and what have you. So they absorb it through their capillaries, and then that water is now part of it is now evaporated, or it transpired. It's now lost, okay, into the atmosphere. The water is lost in form of vapor, water vapor, okay, through tiny openings in the underside of the plant leaves called stomata. Okay, if you watch those video clips for the hydrologic cycle, you will see all this, all these points being highlighted. They form a major segment of the hydrologic cycle. Okay, since about 70% of the precipitation in the US is returned back to the atmosphere as evapotranspiration. You can see that 70% of the precipitation is returned back to the atmosphere as evapotranspiration, meaning only about 30% is like ending up as the groundwater flows or surface flow. Okay, only about 30% is ending up as surface or subsurface flow. 30% is returned back to the atmosphere, okay, via evapotranspiration. So that's what I told you is the main input. Is the main segment or process that contributes to precipitation. Okay. Now, evaporation from free water bodies. Okay, evaporation is a two-phase process. The first phase occurs when the water molecules acquire sufficient energy. They acquire sufficient energy to break through the water surface and escape into the atmosphere. If you remember, we explained in fluid mechanics, the different phases, states of matter, solid, liquid, and gas. We explained that the gaseous phase, the molecules in the gaseous phase, they have higher energy than molecules in the liquid and solid phases. Okay, they have higher energy, and that is why when you want to condense, when you want to change from gas to liquid, they lose a lot of significant amount of energy. Is that clear? So because that energy, they need that energy before they can separate from liquid to gas. Okay, so once they have that energy, they can break through the water surface and escape into the atmosphere. And that energy is supplied, if you have thermal energy, like through increased temperature. That is why, like I said, increasing the temperature will increase the rate of evapotranspiration. Because when you increase the temperature, you are supplying the molecules in water with more energy that they can break, okay? It's sufficient to break through the water surface and escape into the atmosphere. And the second phase consists of transporting the vapor molecules from the vicinity of the water surface into the atmosphere, because vapor is the weight is very negligible, so it's just like fluid. You also have gravity. Gravity, it doesn't mean it is not attracted by gravity, but because of the fact that the weight of the molecules, remember that the molecules in gaseous phase are far from each other. They are not together like those in solid or liquid. If they are together, that is when their overall weight will be higher. But when you have molecule that is micro, the weight of the molecule is micro kilogram, micro newton, very negligible amount. So it will just be floating in the atmosphere. Okay. So they have to be carried away. The second phase is transporting the vapor molecules from the vicinity of the water surface into the atmosphere. The rate of evaporation depends on solar radiation. That is the extent of heat. Now it's about 43 degrees Celsius. So we have, high solar radiation. By high solar radiation, it means the temperature will be higher. When the temperature is higher, the rate of evaporation will also increase. And air temperature, when you have high solar radiation, it will heat the soil or the earth, and the earth will heat the air around it. So the air temperature will increase, which will subsequently increase the rate of evaporation. And atmospheric pressure. Atmospheric pressure is also one of them. And then relative humidity, water temperature, wind speed, quality of water. Okay, quality of water, and then geometry of the evaporating surface. Because when you have, let's say, a flat surface is better than a very, let's say, deep surface, in which the surface area, here we are talking about the surface area, that is the amount of water in contact with the air. Okay, it determines, if you have it in a cup, it's different from when you have it, let's say, in a large basin. So the rate of evaporation increases the geometry. The wind speed, if you have high wind speed, it will increase the rate of evaporation as well. The quality of water, the more the quality of water, the better. Because water of very low quality, because you have a lot of other, let's say, seawater and fresh water. For seawater, you have a lot of dissolved minerals, dissolved salts. Okay, so you will not expect it to have the same rate of evaporation when you compare it with less fresh water that is having less dissolved minerals. So it is the rate is higher when the quality of water is higher as well. Okay, and the water temperature is directly proportional. And I mentioned about the relative humidity now. For the relative humidity, because it means the atmosphere is having a lot of vapor. So that may, that may reduce the rate of evaporation from liquids or from water bodies, because of the fact that there is more or less like a saturation of the water vapor already in the atmosphere. So that may prevent further evaporation from taking place. Okay, and the atmospheric pressure, the higher the atmospheric pressure, the lower the rate of evaporation, of course. But the lower the atmospheric pressure, the higher the rate of evaporation. Because as I explained, if you remember in chapter 3 of fluid mechanics, 233, atmospheric pressure is the volume of air around us. So that volume of air is pressing on the water bodies, okay? And that volume of air, or the pressure it exerts, if it is very high, it will now prevent water molecules from breaking out, okay, from breaking through the water surface. But if you have less pressure acting on the water surface, then the water molecules can easily break through the water surface and escape into the atmosphere. Okay, so this is how the atmospheric pressure affects the rate of evaporation. I also explain the air temperature and the solar radiation. Okay, so you should also understand how each of these affect the rate of evaporation. It's not something that like you sit down and memorize, but simple understanding of the molecular properties, molecular arrangement, molecular structure of water. Okay, that is enough to explain how the rate of evaporation how the rate of evaporation is affected by these factors. Okay. Now, measuring evaporation using pounds. Evaporation is measured in a very simple way. You just, have your pan, put amount of water. After some time, you come and measure it. Okay, and that's it. The most common method of estimating evaporation from a free water body is by means of an evaporation pan. The water surface level is measured daily by a hook gauge, okay, in a sealing well. The evaporation is computed as the difference in the observed levels, adjusted for any precipitation during observation intervals. Meaning, if there is rainfall, it has to be subtracted. Like you have the water level in the evaporation pan, let's assume it is 5 inches. After 2 days, you came back and found that it has reduced to 2 inches. But then there was rainfall. Maybe the rainfall is 1 inch, okay? So you have to subtract that rainfall that has increased the amount of water in your evaporation pan. So that is what that statement means, that you have to adjust for any precipitation during the observation interval. Okay, so this is an example of an evaporation pan. Okay, this is it. Okay, the water inside, and then you have like a gauge, a wear mesh. Okay, and then definitely evaporation takes place. So after some time, you measure, the initial depth, and after some days, you come and measure the final depth, and the difference gives the evaporation. Okay. It has been observed that evaporation occurs more rapidly from a pan than from larger water bodies. Okay, it occurs more rapidly from a pan than from larger water bodies. This is, of course, because of the attraction, the cohesive force between the molecules in larger water bodies, okay, than what you have in the interaction in pan is different from that in larger water bodies. On measuring evaporation, a coefficient is accordingly applied to pan observations to derive the equivalent lake or reservoir evaporation. We use the pan evaporation and then we derive a coefficient and then calculate the lake or reservoir evaporation. Because for lake and reservoir, we cannot measure, the depth, it's not as simple as that of the evaporating pan. So what we do, we derive a coefficient and then you use that to estimate, okay, to estimate the equivalent lake or reservoir evaporation. Pan coefficients are normally computed on an annual basis, but monthly coefficients have also been used. Values range from 0.6 to 0.8 with an average of 0.7. So we normally use 0.7 as the pan coefficient. The pan to lake coefficient is a major cause of error in the pan method. Okay, errors in the range of 10 to 15 of annual estimates and up to 50% for monthly estimates been reported. Preferred for long duration estimates. Okay, it is preferred for long duration estimates. Now, evaporation from a water body is computed using KEP. Okay, K is the pan evaporation coefficient. Okay, EL is the evaporation from a water body. It can be a lake. Okay, and EP is evaporation from the pan. Okay, so we use the evaporation from the pan. We use the pan coefficient to determine lake evaporation or evaporation from any water body. Now, example, find the daily evaporation from a lake for a day on which the observed pan evaporation was 9 millimeter. Okay, so very simple. The observed pan evaporation was 9 millimeter. Okay, and the pan evaporation coefficient is 0.7. Okay, so the lake evaporation will be 6.3. Very simple, straightforward, and direct. Okay, any question? All right. If we don't have any question, now we will take a short break of about 5 minutes, and then take some water, relax, and then we come back to continue. Okay. All right. See you after 5 minutes. Right. Shabab, let's move on. I have posted the lab groups, group 1 and group 2. Okay. And don't forget, when coming today, bring your pen, okay, your calculator, your pencil, eraser, okay, and all that because of the quiz. Okay. Don't come and say, I forgot my calculator, my writing materials or so. Okay. Make sure to bring your writing materials to the class. So let me share. I have already uploaded chapter 4. Okay. I've already uploaded chapter 4. And which is what we will look at now, which is infiltration. Let me share my screen. Okay. You see, in chapter 2, we introduce the hydrologic cycle where we look at the different rainfall processes, different processes making up the hydrologic cycle: precipitation, infiltration, evaporation, evapotranspiration, and what have you. Now we are like taking the different components of the hydrologic cycle and explaining in details by giving all the background information as well as the measurement. Okay, how do we measure each of these processes? We started with precipitation, where we looked at gauge, how to measure it, converting point precipitation to areal precipitation, and then we moved to evapotranspiration, and we looked at how can we estimate evaporation. Okay, now we will move to another process, which is a very important component of the hydrologic cycle, which is infiltration and runoff. Okay, infiltration, infiltrate, the movement of water from the ground surface, okay, into the ground or into the subsurface. Okay, from the ground surface deeper down into the ground. Okay, that is infiltration. And runoff. Okay, if it is saturated, what are the conditions for us to have runoff? That is water moving on the surface, okay, via channels, okay, and what have you. So this is what we are going to consider here, and how do we measure precipitation, okay, or estimate, at least how do we estimate, either mathematically or otherwise. Now, the intended learning outcomes here, the student will be able to explain the process of infiltration and determine the amount of runoff from rainfall using Horton's model. Okay, the amount of runoff from rainfall using Horton's model. Okay, if you watch those two video clips for water cycle, you realize, when you have precipitation, rainfall, okay, you have interception by vegetation, and then water will flow on the surface. Some, depending on the moisture content of the soil, it will infiltrate into the ground, okay? And then some will flow as surface runoff. And then those that infiltrate can percolate deeper to join the groundwater table or water level, okay? And some will flow as through flow to join rivers, okay? And some will seep. We will have seepage. Now, reading please. From this brief explanation, infiltration differs from percolation in that infiltration, here we want to say that the difference between infiltration and percolation is what? Okay, infiltration results from precipitation. B, infiltration results from the penetration of water through the surface layer. C, infiltration refers to the downward movement of water through the porous zone toward the water table. D, all of the above. So What is the answer? Read it, and then I want each one of you to provide answer to this question. So, what is the answer to this question? Type it out. Let me check. I'm coming back to check your answers. I want each one of you to respond. Only 3 of you have responded out of 12. Only 3 have responded. Remaining 9 guys. So I'm waiting. All right. Most of you have chosen C, which is infiltration refers to the downward movement of water through the porous zone toward the water table. Okay, that is C. One person, Abdulaziz of the Firi, is doubting is it B. All right, the answer is B, not C. C is referring to percolation. Okay, C is referring to percolation. If you look at the figure, let me go back to the figure, which I just explained, before explaining this. Infiltration is the movement from the surface, okay? The penetration of water through the surface layer. This is the surface layer into the ground, okay? That is the first stage. That is infiltration. And then when it moves again, okay, the downward movement of water through the porous zone towards the water table. This is the water table, okay? So towards the water table, this is now percolation, okay? This is percolation. Is that clear? So percolation is different from infiltration, okay? It's also infiltration, but refers to the downward movement of water through the porous zone toward the water table, while infiltration is just the penetration of water through the surface layer, okay? Through the surface layer. All right. Let me move on. Reading quiz. Okay, we already took this reading quiz. Now, the process of water penetration through the surface layer is known as infiltration. Okay, it must be distinguished from the process of percolation, which I explained, which describes the downward movement of water through the porous zone, okay, toward the water table. Okay, the water table is just like the river flowing underground. Okay, it's like the river flowing underground. We have an underground river flowing, which constitutes the groundwater flow. Okay, this we will also look into, I think, in chapter 6. Yeah, chapter 6 also. The infiltration rate through the surface is dependent on the soil surface conditions as well as the rain characteristics. Okay, of course, if the soil is saturated, you will not have any appreciable infiltration. But if it is not saturated, you will have appreciable infiltration. And also, it depends on the porosity of the soil. Okay, if the soil is highly porous, okay, then water can easily move between the pore spaces. Okay, the pore spaces of the soil grains. Okay, and also it depends on the rainfall characteristics. Okay, this will the rainfall intensity as well. Okay, but the rainfall duration, the intensity, all this will affect infiltration. Other soil surface conditions affecting infiltration include compaction. The more compact the soil is, the less the infiltration. Okay, the less compact, because compaction here refers to, aggregation, coming together of the soil particles very close to one another, such that the porosity of the soil will be greatly reduced in that case. Okay. Now, cracks, slopes, degree of cultivation and degree of urbanization. Okay, cracks, if you have many cracks, then water can easily pass through those cracks. Okay, and then if you have slope, because of gravity, it can easily, if it is slopy, the infiltration may be less because water will run off. Okay, you will just have run off. It will not stay for appreciable amount of time for it to like soak and then infiltrate well. It will just like go down, due to gravity because of the slope. And then degree of cultivation. If the place is well cultivated, you have a lot of good soil there, and then there will be a lot of vegetation that will retain the water when it rains. Okay, and then degree of urbanization. For urbanization, that is the extent of converting, let's say, small towns into urban centers. Okay, for urban centers, normally because of pavement, you have a lot of tiles, a lot of buildings, a lot of structures that will prevent infiltration. Okay, a lot of structures that will prevent infiltration, a lot of roads, a lot of this and that will reduce the exposure of the ground surface to precipitation. So a degree of urbanization also affects the rate of infiltration. Okay. Now, infiltration capacity. Infiltration capacity is an aspect of infiltration that is associated with the soil. Okay, it is defined as the maximum rate at which water can be absorbed under a given condition. The maximum rate at which water can be absorbed under a given condition. So more or less like the saturation capacity of soil. Okay, so the maximum rate at which water can be absorbed under a given condition. Because once the infiltration capacity is reached, then it can no longer absorb any water. So you must have surface runoff in that case. Okay. You see, soil is very important for all engineering purposes, most especially civil engineering design aspect. Okay, because of course civil engineers design structures on ground. They don't design structures in the atmosphere, just hanging without touching the soil, without touching the ground surface. Okay, so all structures, all areas of civil engineering, okay, are dependent on soil. Okay, everything begins with the soil. Okay, it begins survey, and then you have the soil characterization. Take it for instance, okay, the structural engineering. Before you build anything, you have to carry out soil testing, soil bearing capacity, to know that whether that soil has the adequate strength to carry the structure, the building that you want to design. Is that clear? If you look at transportation, okay, it begins with the soil, because you have to build road networks on soil, bridges, and then you have culverts, you have overhead bypass and what have you. All these, their foundation, they go deep down into the soil. You have the environmental engineering processes, the water treatment plant and what have you. They all have to do with soil, because if you look at the source of water, usually which is either surface water or groundwater, it also has to do with soil. And the source of water also determines how quality the water is as well. Okay, and then coming down to the water engineering aspect, which is also having to do with soil. There you have the groundwater hydrology, which we are going to look into in chapter 6. Okay, what is the hydraulics of the groundwater? Okay, how does water flow in the subsurface? We will introduce you to some of the aspect of the groundwater hydraulics in chapter 6, whereas there is another course in the electives, the senior elective. If you find it interesting, you can take groundwater hydrology, where you will have detailed explanation about the groundwater flow. Okay, so everything the civil engineer does, it begins from the soil. Okay, it begins from the soil. So the soil is very important. And then you have, of course, the geotechnical engineering, which is another aspect of the civil engineering that specifically specialize about the soil, okay, the soil properties, the soil strength, the bearing capacity, so that, I mean, you will take the geotechnical engineering, I think, in next time. Next time, you also have the soil mechanics, okay, the soil mechanics, okay, and fluid mechanics is also prerequisite to soil mechanics, because you have soil flowing in the subsurface, so you must understand the fluid mechanics before you can, you know, comprehend well, I mean, the soil mechanics. So soil is very important. That is what I'm trying to say in summary, okay? And understanding the property of the soil and the soil mechanics is, I mean, is very, very important, okay? So it is defined as the maximum rate at which water can be absorbed under a given condition. That is the infiltration capacity. The greater the infiltration capacity of the soil, the greater the amount of rain that can be absorbed by the soil. Because once the infiltration capacity is reached, it means it can no longer absorb any water. So if the infiltration capacity is high, then it means that it can absorb higher amount of water. Okay. Direct runoff from rainfall or rain excess. Infiltration and rainfall are very related, you know, are related together in such a way that, you know, when the soil is saturated, when the infiltration capacity is reached, it can no longer infiltrate, isn't it? So it has to flow as runoff. So runoff begins when you have the infiltration capacity of soil being reached, okay, which is called direct runoff or rainfall excess. All these are referring to the same thing. Direct runoff or rainfall excess. They are all synonymous. So direct runoff or rainfall excess contributing to immediate stream flow, because the runoff flows on the surface until it reaches stream, river, or even the ocean, okay, or sea. Contributing to immediate stream flow is assessed by, don't forget the difference between ocean and sea. Okay, although very simple, but as water engineering students, you need to understand the difference between an ocean and a sea. Direct runoff or rainfall excess contributing to immediate stream flow is assessed by subtracting the infiltration from the rainfall. Simple. You have infiltration, you have rainfall, which is precipitation, and then you have infiltration. When infiltration is deducted from precipitation, the remaining has to flow as runoff. So runoff is simply precipitation minus infiltration, okay? Meaning precipitation is equal to runoff plus infiltration. When rain falls, okay, it infiltrates into the ground, okay, or it runs on the surface. Very simple equation, okay? So that is what we are saying here, that the direct runoff, which is R in this case, contributing to immediate stream flow, is assessed by subtracting the infiltration from the rainfall, subtracting infiltration from I from P, simple, when there is no short-term evapotranspiration, when it has been adjusted, or when it has been adjusted for evapotranspiration. So this is the case when there is no short-term evaporation or evapotranspiration, or when it has been adjusted, okay? That is, we don't have evaporation or evapotranspiration. That is if we neglect it, or it has been adjusted for the evapotranspiration. So in that case, all rainfall is ending up as either infiltration or runoff, okay? Now, let me... Now, the infiltration is I, when I, okay, here we are explaining the figure, the next figure, there are three distinct cases of infiltration. Three distinct cases of infiltration. I will explain these three distinct cases using this curve. Okay, we will use this curve, which is figure 4.1, infiltration behavior under different rainfall conditions. Infiltration behavior under different rainfall conditions. Okay, so we'll be explaining this curve here. Okay, there are three distinct cases of infiltration. Okay, so if you look at the figure, you have time on the x-axis and you have infiltration rate, which is F. Okay, infiltration rate. Infiltration rate is also having almost the same unit as rainfall rate. Okay, rainfall rate is in inch per centimeter, or no, inch per hour, or let's say length or depth per time. Okay, depth per time. The same thing with the infiltration rate. Okay, so if you look at the figure, okay, you have I less than Ks. Okay, I less than Ks, which is the rainfall intensity. I is the rainfall intensity. Okay, I is the rainfall intensity, and Ks is the saturated soil hydraulic conductivity. Okay, is the saturated soil hydraulic conductivity. Okay, soil hydraulic conductivity is more or less, the capacity of the soil to allow water to pass through it. That's the hydraulic conductivity. We'll explain the soil hydraulic conductivity in great details in chapter 6 under groundwater hydrology. Okay, but for now, I will just give you the simplest main definition, so that when we reach that area, I will give you all the the detailed explanation, as well as the computational methods to be used for the estimation of the soil hydraulic conductivity. Okay, it is the soil saturated hydraulic conductivity. Okay, which simply tells us about the ease, how easily water can pass through the soil. Okay, how easily water can pass through the soil. Okay, and I is the rainfall intensity, which I explained. Okay, the rainfall intensity, which is in depth per time. Okay, so it can be in inch per centimeter or millimeter. Let's say millimeter per hour. Okay. So now, the first instance that we are looking at is when the infiltration capacity or rainfall intensity is less than the soil saturated hydraulic conductivity, which is Ks. Okay, and I told you the soil saturated hydraulic conductivity is the ease with which water pass through the soil. Okay, and in this case, if the infiltration capacity is less than the soil saturated hydraulic conductivity, all rainfall infiltrates. Okay, all rainfall infiltrates, as shown by line 1 in figure 4. Okay, let me take you to line 1. Line 2, 3, and 1. Okay, this is line 1, if you see it here. Okay, so in this case, if the rainfall intensity is less than the soil saturated hydraulic conductivity, all rainfall is infiltrated. Okay, all rainfall infiltrates into the soil. Okay, so in that case, the infiltration rate, okay, becomes constant. Okay, it becomes just one value, because all rainfall just goes into the soil, all the rainfall. Okay, So for all the rainfall duration, the total amount, the infiltration capacity is just a constant value. Okay, and then we have a case whereby the infiltration capacity is greater than the soil hydraulic conductivity. Okay, if this happens, then what that means is that initially water infiltrates at the application rate after a time TP. Okay, after a time TP, which is indicated, I will show it on the figure. Then the capacity of soil to infiltrate water falls below the fall rate. Surface ponding begins, which results in depression storage and runoff. Curve 2. Let me explain it using the curve. We explained the first one. That is when the rainfall intensity is greater than the soil hydraulic conductivity. We say that all rainfall infiltrates into the soil, and we explain it using this figure. Okay, line 1. Now we have the second case, that is when the rainfall intensity is greater. Line 1 is when I is less than Ks. Line 2 is when I is greater than Ks. And what happens when the infiltration capacity or when the rainfall intensity is greater than the soil hydraulic conductivity? When it is greater than the soil hydraulic conductivity, I told you the soil hydraulic conductivity is the ease. Okay, how can water pass through the soil, so easily? Okay, so the greater the value, the more easily the water passes through the soil. Okay, so here in this case, what we are saying is that if the rainfall intensity is greater than the soil hydraulic conductivity, what happens at the beginning? Water infiltrates at the application rate. So it infiltrates, like you see, up to this point, up to TP. Okay, so it infiltrates, but then it will now saturate the soil. Okay, it will now saturate the soil, and when the soil is saturated, that is when the hydraulic conductivity of the infiltration capacity of the soil is reached. So that is the capacity of the soil to infiltrate water falls below the rainfall rate. Okay, and in that case, rainfall will begin to accumulate. There will be surface ponding, okay, which will result in depression, storage, and runoff. So in this case, it will reduce. Okay, that's when you have it this way. Okay, it will now reduce until it becomes constant. Okay, so rainfall will no longer be infiltrating, and it will now be retained on the surface as ponding. Okay, it will form depression storage. Okay, then will decrease until the soil bearing capacity, the soil capacity now is equal to the saturation, the soil hydraulic conductivity. Okay. So, like I said, it approaches a constant rate, which is FC, okay, which is the infiltration rate capacity approaches a constant rate, okay, because it is equal to now the soil saturated hydraulic conductivity. Now you have curve 3 as well. Curve 3. For curve 3, you also have the same condition as curve 2, that is I greater than Ks. From the beginning, water is always ponded on the surface. Okay, in this case, water is always ponded on the surface. It's always ponded on the surface, and there is no infiltration. Okay, so this is one. Okay, that is ponded infiltration. You can see it. It's always ponded on the surface. Now, for a continuous uniform rain of intensity I, the surface runoff hydrograph has a shape indicated by Q. For a continuous uniform rain of intensity I, the surface runoff hydrograph. Hydrograph is simply a plot of the rainfall intensity versus time. Okay, what is the rainfall intensity over time? So the surface runoff hydrograph has a shape indicated by Q. Okay, so this the surface runoff hydrograph, okay, indicated by Q. Okay, and this is the rainfall intensity. Okay, for a uniform rainfall intensity. So that's why we say for a uniform rainfall intensity, and that's you can see it inch per hour. Inch per hour. But actually, when writing unit, nowadays scientists, they discourage the use of dot after unit like inch. Okay, rather than writing in dot, just write it as in without the dot, except the unit comes, at the end of a sentence where you should have a full stop. So here you have a constant rainfall intensity I, okay, which is 5 inch per hour, and this is the rainfall intensity, okay, and this is I minus Q, okay, rainfall intensity minus the runoff hydrograph. Now the difference between the dotted, okay, I minus Q curve and the rainfall, the infiltration rate, which is FP curve, signifies interception and other minor losses, that is storage at the beginning. After the surface storage is filled in, the two curves coincide. Okay, the two curves coincide. Okay, that is FP and this one. Okay, so the difference, which is this, is indicative of the interception, okay, and other minor losses. After the surface storage is filled, okay, the two curves coincide. You see, they remain the same and move on. Because once you have the surface storage, the interception and other minor losses at the beginning, then they move on together. Now, the Horton's model. This is equal to. Horton in 1939 presented a three-parameter equation expressed as P, okay, that is the rainfall, the soil capacity given by F naught, which is the initial infiltration capacity, minus FC. FC is the final or constant infiltration capacity or field capacity. Okay, which is the final or constant infiltration capacity. And then K is a factor representing the rate of decrease in the capacity. It's a factor representing the rate of decrease in the capacity because the infiltration capacity decreases over time. Okay? When it rains, soil will begin to absorb, water will begin to infiltrate. But after some time, once the soil saturated hydraulic conductivity is reached, then there will no longer be infiltration. Okay, so it decreases, the infiltration capacity decreases. So K is a factor representing the rate of decrease in the capacity, which is per time. The parameters of the equation here, because FC is a constant, it's a constant infiltration capacity. So the parameters here are basically the initial infiltration capacity, which is F naught, and K. Okay, T is the time. Okay, T is time. Have no physical basis, that is, they cannot be determined from soil water properties and must be ascertained from experimental data. Okay, E here is exponential. So this is the Horton's three-parameter equation. This is the Horton's three-parameter equation, which we will be using in estimating the soil infiltration capacity, which is FP. this equation, the Horton's equation, when plotted, plot of equation 0.2 is an asymptotic curve that starts from F naught. Okay. It's an asymptotic curve that starts from F naught and attains a constant value of Fc. Okay, it starts from F naught, infiltration capacity, okay, which reduces, okay, over time. It attains a constant value of Fc. This is Fc, which is the field capacity, which is the maximum infiltration capacity, okay, or the constant infiltration capacity, the infiltration capacity, okay, and this is shown by ABD, ABD, okay, so this dashed curve. Oh, my time is up. All right, so in the next class, we'll continue from the Horton's model, and we will apply the Horton's model in solving an example, okay? And then we move on to the next chapter. So any question before we call it a day? All right, if you don't have any question, I have already uploaded this figure, this slide. I have already uploaded it on the Blackboard. And like I said, I have already also uploaded the groupings, the two groups, okay? The quiz will be theory. It will be everything. It will be everything. Chapter 1. Okay, it will be chapter 1. Of course, we have numerical problems. Definitely. Definitely there will be numerical problems. Definitely, okay, which will test your understanding of the theory. Yeah, it will test your understanding of the theory. Okay, so if you don't have any question, see you at 2 o'clock. The first group will be coming in. We will start at 2. You see, they made a mistake and they wrote the second group will be starting at 3:30. No, the second group will start at 3:20. Okay, the second group will be starting at 3:20. So the second group should be available by 3:20. They should come in. Okay. All right. See you. Bye bye.
Doctor,
Yes.
the group 2
Yes.
start at 3:20 or 3:30?
No, it's supposed to be 3:20, not 3:30, because we have the lab hours is 2 hours 40 minutes. So when you divide it into 2, you have 1 hour 20 minutes. Okay. 1 hour 20 minutes. It will be from 2 to 3:20. Okay. So the second group will start from 3:20 till 4:40. That is 1 hour 20 minutes. Okay. Yeah. Thank you.